Once upon a time, in somewhere far, far away, there is a big island and a remote island village nearby it. The remote island village and the main island is connected with a rope suspension bridge and are separated by a river. The villagers in a remote island relies heavily on the bridge to cross to the main island. Every morning, the children will use the bridge to go to school. In a rainy day, the bridge was broken after getting struck by the lightning. As a result, the remote island is separated completely from the main island. The villagers are struggling to get children to school every day and to get their produce across the river. The broken bridge has caused the villagers a lot of problems as there is no way to reach to the other side of the bridge.
The first step is to identify the problem. In this case, the problem is the rope suspension bridge is broken, and this will lead to sub-problems such as the villagers are struggling to get their produce to the market across the river, there's no way to get their children to school every day, and this will lead to zero interaction between the remote island village and the main island. Next is the decomposition of the problem. The broken bridge may be caused by three possible factors, which are the frequency of usage of the bridge, the weather, and the overloading of the bridge. As mentioned earlier, the bridge is heavily utilized as it is the only way to get across the river. Secondly, the extreme weather, heat and temperature may cause the rope to be brittle and break. Thirdly, the overloading of the bridge may cause big tension to act upon the bridge. For data evaluation, we will be evaluating the best and worst design of a bridge. The K-truss bridge is one of the best design of the bridges. The idea of K-truss bridge is to break up the vertical members into smaller sections, which will distribute the tension and force evenly. The not-so-good bridge design is the suspension bridge. The Tacoma Narrow Bridge were twisted and buckled in the wind before collapsing. For abstraction part, in order to come up with a solution to the problem, one must first understand the design of the bridge that broke. In the old rope suspension bridge design, we can observe that the most of the weight are supported by 4 towers, and this will pass the compression forces from the rope directly to the ground. The suspender moves the dash compression force to the tower through the ropes, which will make the force at work to be balanced on each side of the bridge. After knowing the design of the bridge, we need to know what material is used in building the bridge. In this case, the main material used are rope, which is probably polyester or nylon. Next is the component that made up 90% of the bridge, which is wood, and it's preferably laminated timber. Next, the knots used in tying the woods up into the bridge are the pioneering knot, rope bridge knots, and bamboo lashing. The algorithm in this challenge is to first identify the problem, decompose the problem, abstraction, algorithm, modeling, and evaluate error. In this case, the problem is the broken bridge, and we figure out the possible reason that caused the bridge to break. Before designing a bridge, we need to find out which bridge design works and which doesn't. Once we are done with that, we go in depth into the design of the old rope suspension bridge and proceed to plan and make the model of the new bridge. Then, we evaluate the error. Proceed into the modeling part. It shows the general design of the bridge. This design is inspired by the K-truss bridge that we have discussed earlier. By folding the paper into fan shape, it represents the vertical member which will allow the tension and force to be distributed evenly throughout the bridge. For the error part, I identify one error which is the poorly distributed force and tension. In the old rope suspension bridge, all the forces and tension are absorbed by the rope and the woods that hold the bridge together. A large volume of users on the bridge may cause the rope to reach its maximum capacity and breaks eventually.
We will be making a bridge out of 2 A4 papers and 6 inches of tape, as you can see on the screen. And the materials that we're gonna need are 20-cent coins, 2 pieces of A4 papers, scissors, pen, ruler, and 6 inches of tape. First of all, we need to fold the paper into 4 parts vertically and cut them off with a ruler. Proceed to do that for the rest of the A4 paper. And you have something like this. Next, fold the papers into half like how you always do when making a paper fan. You need to repeat the whole process for 4 more times because you need 5 of these paper fan. Use the tape to tape all 5 pieces of the fan together and you will have something like this. After that, measure the length and width of the fan to make the top and bottom part of the bridge. After measuring the length and the width of the fan, mark the measurement in the paper and fold it accordingly. Use a ruler to make sure that the lines folded are in a straight line. After finish folding all sides of the bridge body, use a ruler to cut the excess off. Since the length of the A4 paper is less than 14 inches, we need to manually extend it with the excess paper that we have. Once that is done, tape the fans onto the bridge body together. This includes the sides of the bridge body as well. We need to ensure that the side of the bridge body is secure. And our paper bridge is done. Once the bridge is done, the bridge is then measured again to ensure that it is a proper length of 14 inches. Before testing the bridge out, both ends of the bridge are taped onto the book to secure it. For the first trial, we'll be using both the old and the new 10-cent coins. As you can see, I arranged the coin by rows on both ends of the bridge and alternate the use of old coins and new coins to balance the weight out throughout the bridge. Once the coins are arranged until the middle part of the bridge, we can clearly see that the bridge curved downwards, and upon adding more coins on the middle part, the bridge then collapsed. The result of the first trial revealed that the bridge can only take up to 28 new 10-cent coins and 24 old 10-cent coins before it collapsed. For the second trial, we'll only be using new 10-cent coins. By using the same arrangement technique that we have used in the first trial, the coins are arranged on both ends of the bridge to ensure that the weights are distributed evenly. We can clearly see that although the shape of the bridge is distorted due to the weight of the coins, it does not rupture right away.